So we have just a couple of things left to deal with in section 7.2, and I think I'm just going to jump right into an example. So if I take the sine of the cosine inverse of x plus the tangent inverse of y. Something like this, where we're combining trig expressions with inverse trig expressions. We've got some addition in there, so we're going to need an addition formula. Now, if I want to figure out this cosine inverse of x and tangent inverse of y, here's how I want to deal with this. If I just use the addition formula for sine, it's going to get messy pretty quick. So I'm going to introduce some new notation. So we know that for this, I'm plugging in some number x, cosine inverse should spit out an angle. Same thing with plugging in some number y, and tangent inverse spitting out an angle. So I'm going to say theta cosine inverse x. This is a Greek phi, also commonly used to reference angles. Tangent inverse of y. So this breaks down into sine of theta cosine of phi plus cosine theta sine of phi. Well, sine of theta and cosine of theta, cosine of phi, and sine of phi can all be figured out if I look at the correct triangles. So if I start with a triangle with x and 1, there's my theta right there. Because cosine of theta will be x over 1, just x. So we know that the inverse cosine of x is equal to theta. And then I can finish using the Pythagorean theorem to get square root of 1 minus x squared for that other side. Well, that tells me right away that sine of theta can be calculated square root of 1 minus x squared. Taking the second triangle, the sides 1 and y, angle phi down there, tangent of phi is just going to be y, which fits with up here tangent inverse of y equaling phi. Go ahead and solve for the hypotenuse to get the square root of 1 plus y squared on the hypotenuse. And then we have cosine of phi, 1 over square root 1 plus y squared, and sine of phi, y over square root 1 plus y squared. So we've got all the necessary parts here to go ahead, plug into this formula here, and we're left with sine of theta plus phi is equal to square root 1 plus x squared. That's sine of theta cosine phi, 1 over square root 1 plus y squared. Oops. 1 plus should have been 1 minus. And then for the second piece, cosine theta sine of phi, cosine theta is just x, so plus x, and the sine of phi, y over square root 1 plus y squared. So, able to sort the whole thing out, even though we had this rather complicated expression involving inverse trig functions in it. A little substitution to keep track of these inverse functions, really mostly about shortening up this expression so it was easy to write. But back with what we worked on last chapter about inverse trig functions, how they relate to right triangles, we were able to find precise values for these things. And notice I did never have to know what x and y were. I still got this formula in terms of both x and y. So one more example just to show you how we can work with some of these things. Take an expression, let's do 1/2 sine x plus root 3 over 2 cosine x. Now what would be great is if I can turn this into something that looks like one of my additive identities. The addition here, it's a little bit weird, right? The addition is in between these two things, so it's not like I've got sine of x plus y or cosine of x minus y or anything like that. But what I do have is this 1/2 and this root 3 over 2. And those, conveniently enough, can be expressed in terms of trig functions. So if I add a couple of variables, let's say theta is equal to pi over 3. Well, cosine theta is then 1/2, which I have right here. And sine theta is equal to square root 3 over 2, which I have right here. Well, that means I can rewrite this as cosine theta times sine of x plus sine theta times cosine x. Now they're in a different order from what we were used to, but I should be able to rewrite this using my identity. So going in the other direction, this is going to be sine of x plus theta. I can break that apart right there, and it worked because this 1/2 and root 3 over 2 were values that I knew what angle would spit out those values when I applied trig functions to it. So that was a convenient happenstance in this case. Now, if the coefficients are not, really nice numbers where you know what angles to use, that's okay. Your book goes through the derivation of this too, but you can work it out with Pythagorean theorem that if you've got a sine x plus b cosine x. So really, this one we started with on the last example was of that form. And if you've got that, we're going to introduce a couple of things. K square root of a squared plus b squared. We build a nice triangle. And find an angle phi such that cosine phi a over square root a squared plus b squared and sine of phi equals b a squared plus b squared. Hopefully you recognize these are the forms of sine and cosine. If you've got a triangle, with phi down there, right triangle like that, with angle phi down in the corner, that's exactly where those are going to come from. If you can find that, then a sine x plus b cosine x, it works out to k sine of x plus phi. So, your book has a couple of examples of that, and there will be a few of those coming up in the homework. So, we will be moving on to section 7.3 after this.